The robot arm, welding a car body on a factory line, has no eyes. No cameras pointed at the car. It cannot see the metal it welds. And yet, 1,000 times a shift, it drives its tip to the exact same spot, within a fraction of a millimeter, tighter than any human welder alive. So how does something blind know exactly where its own hand is in space? It isn't looking, it's counting. Every joint knows its own precise angle, and pure math turns those angles into a point in the air. Once you see how, you'll never look at a factory the same way. Start with a single joint. Inside it is a servomotor, an electric motor built for one thing: to turn to an exact angle and hold it there no matter what's pushing back. But a motor alone is dumb. It has no idea where it's pointing. So bolted to the shaft of every joint is the real hero of this story: an encoder. An encoder is a sensor whose only job is to measure angle. The common kind is a disc with a fine pattern etched around it, read by a light sensor as the disc spins. As the joint rotates, the encoder counts the pattern ticking past, and those ticks translate straight into degrees, splitting a single rotation into millions of steps, far finer than a human eye could ever judge. So the joint isn't guessing. At every instant, it reports the exact angle it's sitting at. The better modern arms use an absolute encoder, which knows its angle the moment you switch the power on, without moving to find a reference. 6 joints, 6 encoders, and the robot always knows, precisely, the pose of every one of its own hinges. Now, why do these arms almost always have exactly 6 joints? Not 5, not 8, 6. There's a beautiful reason. Think about what it takes to put something anywhere in space. First, you need position. How far left, right? How far forward, back? How far up, down? That's 3 numbers, 3 directions. But position alone isn't enough. A welder or a gripper also has to be pointed the right way. Picture holding a pen at a fixed point in the air. You can still tilt it, roll it, and swing it to aim the tip in any direction. That's 3 more numbers, 3 ways to rotate. 3 for position, 3 for orientation, 6 numbers total to place a tool anywhere, aimed any way. Engineers call these the 6 degrees of freedom. And here's the payoff. To independently control 6 things, you need 6 joints. Give an arm 6 good joints, and it can reach any reachable point at any angle, the way your shoulder, elbow, and wrist team up to put your hand flat against a wall or twist in behind your back. Fewer than 6, and there are poses it simply cannot strike. 6 is the minimum that unlocks total freedom, which is why it became the industry standard. So the arm knows all 6 of its joint angles. How does that become a point in space? This is where the math earns its keep. The easy direction is called forward kinematics. You know all 6 angles, and you want to know where the tip ended up. That's just geometry. The length of each arm segment is fixed and known. Stack the segments up, bend each one by its measured angle, and you can calculate exactly where the tip lands and which way it's pointing. Angles in, position out, instantly. But that's backwards from what you actually want. In real life, you don't say, set joint 3 to 41 degrees. You say, put the welding tip right here, tilted like this. Now you work the problem in reverse. Given the target point and angle, what does each of the 6 joints need to be? That's inverse kinematics, and it's the hard one. There can be several different joint combinations that all reach the same spot. Think of the many ways your elbow can sit while your fingertip stays put. And the controller has to solve for a valid set thousands of times a second as it sweeps along a path. That solver is the real brain that turns go there into 6 exact angles. No eyes required, just geometry and known lengths. Here's a distinction that trips up almost everyone, and it's the honest heart of how these machines behave. There are 2 kinds of good aim, and industrial arms are freakishly strong at one and surprisingly weak at the other. The first is repeatability. If you send the arm back to a spot it has been before, how tightly does it return? Industrial arms are astonishing here, often repeating to within a few hundredths of a millimeter, thinner than a human hair. landing on the same spec every single time. The second is accuracy. If you give the arm a fresh coordinate it has never visited and say, "Go exactly there," how close does it get to that true position? Noticeably worse. It might be off by most of a millimeter or more. Tiny flexes in the metal, gear slack, temperature, model versus reality mismatch, all of it adds up. So the trick the car industry leans on is this: don't rely on accuracy, rely on repeatability. You don't feed a welding robot raw coordinates. You physically show it each spot once, it memorizes that pose, and it repeats that exact motion flawlessly forever. It's blind, but it's a perfect creature of habit. Everything so far gets the wrist to the right place, aimed the right way. But a robot arm isn't a robot on its own. The tool bolted to the end is where the actual work happens, and it's swappable. Engineers call it the end effector. Change the end effector, and you change the entire job. Bolt on a welding torch, and it builds car bodies. Bolt on a gripper, and it picks parts off a line. Bolt on suction cups, and it lifts a pane of glass by vacuum alone. Bolt on a nozzle, and it sprays an even coat of paint. Same 6 joints, same encoders, same math underneath. The arm is a general-purpose positioner. The hand decides what it's for. That's why one arm design shows up doing 100 different jobs across a factory. So if the arm is a blind creature of habit, how does it learn the habit in the first place? Mostly, a human walks it through using a handheld controller called a teach pendant. An operator holds the pendant and jogs the arm, nudging each joint until the tip sits exactly on the first weld point. Save it. Jog to the next point, save it. Point by point they trace the whole job by hand, and the robot records the precise joint angles at every saved position. Press play, and it strings those points into a smooth, repeatable path, running it identically shift after shift, simulating the whole path in software first, then loading it onto the real arm. But the core idea is the same. You are not writing the robot a description of the car. You are burning in a sequence of exact poses and telling it, "Do this, exactly this, forever." Now the consequence nobody expects, and it follows from everything we said. The robot is only counting its own joints. It is not checking whether the car is actually there. So if the car body is misaligned, or the line hiccups and no car shows up at all, the robot doesn't know and doesn't care. It drives to its memorized points and fires the welder into empty air. Flawlessly, right on schedule, welding nothing. Blind repetition is a superpower and a liability in the same breath. That's why the machine never works alone. The car is clamped into precision fixtures, heavy jigs that force every body into the exact same position, so the robot's memorized points always line up with real metal. The fixtures do the seeing, so the robot doesn't have to. And when parts vary too much for fixtures to guarantee, that's when engineers finally bolt on cameras, machine vision that lets the arm find a part and adjust. But notice, vision is the exception you add when blind repetition isn't enough, not how the machine works by default. The default is count and trust the world to be where you left it. A blind counting machine sounds foolproof. It isn't. Here are the honest trade-offs. Fragility. Because it trusts its own count and not the world, small surprises break it. Drift the car a few millimeters, let a part slip in the gripper, and it plows ahead confidently doing the wrong thing. It has zero common sense, and it can't notice something looks off because it isn't looking. Danger. This arm is fast, heavy, and strong enough to throw a chunk of steel across a room. And it moves exactly as programmed, whether or not a person is in the path. It doesn't feel you there. That's why classic industrial arms live inside safety cages with interlocked doors that cut power the instant anyone reaches in. Newer collaborative arms are built softer and slower, with force sensing to stop on contact. But that safety costs you speed and payload. Limits. Every arm has a fixed reach and a payload limit. Only so much weight before precision collapses or the motors overload. Ask it to lift beyond spec, and the beautiful repeatability goes out the window. Cost and rigidity. A capable arm plus its tooling, fixtures, safety, and programming is a serious investment. Happiest doing the same job a million times. Change the product, and you often have to refixture, reteach, and retune. It's a specialist, not a handyman. So let's kill the two big myths. Myth 1. A factory robot must see what it's doing. It usually doesn't. It knows where its hand is purely because every joint counts its own angle, and math does the rest. The seeing, when it exists, is a bolt-on extra. Myth 2. It's smart. It isn't. It's a blind, brilliant counter with no idea what a car is. It memorizes exact poses and repeats them to a hair's width forever, trusting fixtures and humans to keep the world lined up around it. That's the whole trick. 6 joints, 6 encoders counting angles, 1 math problem solved thousands of times a second, and a tool at the end doing the work. Blind, tireless, and more precise than any hand alive, not because it looks, but because it counts. Subscribe to Whambox for more how does it actually work explainers.